Awesome. Welcome, everybody, to the Point One live stream. In today's session, Demystifying Network RTK, we're going to drill into the two primary methods of delivering centimeter-level accuracy: single baseline, and as the title said, network RTK. Our goal throughout this conversation is to cut through a lot of the industry and marketing jargon, as well as some of the FUD out there, to give you a much clearer picture of what these technologies are and how they work. My name is Tom Weeks. I'll be the host today. I am honored to have Aaron Nathan here. Aaron is the founder and CEO of Point One. He is a recovering robotics enthusiast, or robotics nerd, as I like to say. And he is truly a recognized expert in all things localization. So thanks for being in, Aaron.
Thanks for having me.
We'll try to get the discussion to a really crisp 30 minutes, covering about 6 or 7 topics here. And then after that, I actually have a surprise questionnaire for Aaron that he knows nothing about. I promise you that. So hopefully you'll stick around and be here for that fun. And then we'll take a few questions at the end. So Aaron, I think the best way to start here is, why don't you just give a kind of succinct definition of what is single baseline, and almost more importantly then, what is network RTK?
Yeah, no, 100%. And ultimately you said it at the top, these are all different ways that you can make GPS way more accurate than just what you'd get by itself. And so ultimately you need to get a correction signal of some kind. And when you look at single baseline, this is kind of the gold standard. It's the way that this whole technology started, where I have a fixed point on Earth, I know where it is, I put a GPS receiver there, I know its location very accurately, and then I can solve another location that's, we'll say, close by within centimeters, because I happen to know a lot of information about that single base station. So single base basically means that there is a single base station you're using to correct GPS.
And Justin, let me inject something here too, because we'll touch on this later. This is where the term OSR comes from. They're observables.
Yes. And so the term like observables is GPS speak for, it's the raw data that comes out of your GPS receiver. So GPS receivers, they're generally measuring this loosely, the distance to the satellites, and you'll have effectively 2 measurements for each satellite signal that you receive, and those are the observations. It's literally what the receiver is hearing from the satellites. And so the idea of the OSR is that you can think about manipulating or using those observations in order to calculate a high precision location. So back to the single baseline definition, you're really looking at a difference between the observations on that base station and the observations on what we call the rover, or the thing that you care about. And that's the high level difference.
Cool. And so network RTK then, how is that different from single baseline?
Yeah, so network RTK is a more advanced concept, but basically uses the same principles. So instead of a single base, you end up with multiple base stations in a network. And so they are usually connected up to, let's say, like the internet or some other backbone. And then there's a central server that is taking all of the data from several of these known base station locations. And then when you connect as a user, that server is effectively interpolating the data for you and then synthesizing a fake base station location, and then sending it back to you as a rover as observations that came from this synthetic place that the server generated for you. The theory is that by effectively taking all of that data together from a network of stations, you can have a longer distance from a single point that still represents, what is actually happening in the location that you're in.
Awesome. So is it fair to say then, in my terminology, that network RTK is it an algorithmic-based approach for, I'm going to use the word guessing, at what the observables would be in a location.
Yeah, you can definitely say that. The idea is that it's the way I would put it is a geometric-based way of looking at the problem, where I'm still looking at observables, so like those measurements coming off of a series of base stations, and I'm more or less figuring out how to interpolate between them using the geometry of those
geometry.
stations. Yeah.
Great segue then is, because a little bit of a tangent, but it is something that really confused me at the beginning. So SSR solutions sound like there's something similar to this, but they only provide decimeter level precision. What is the difference between this interpolation, and maybe that's geometric, and maybe the SSR is something different?
Yeah.
Help us understand that.
Yeah, so SSR is yet another technique, and what SSR does is you still have a network of base stations, but instead of looking at the raw observations and trying to do something, you actually try to break down the problem into the physics behind what is happening in the GPS satellites, the ionosphere, the troposphere, basically all these components that ultimately create the errors that we're trying to cancel out in the first place. So one way to think of it, like you said, is network RTK is like a geometric way of interpolating between the stations. SSR, on the other hand, is using more or less a physics-based model to figure out how do I do more or less the same thing, which is synthesize these kind of fake or virtual observations that can be sent to my rover to calculate RTK. And I mean, the real obvious question is like, well, why would you do one or the other? So the main benefit for SSR is that theoretically you can have fewer base stations because these physics models let you interpolate further. That is true most of the time when physics is represented by the equations that we've actually used in those models. And this is always kind of the trade of nothing beats having more data. And that's what network RTK is really powerful in the sense that it's just using a simple geometric overlay. And so this is much more predictable and honestly something that, while much less complex from a physics perspective, tends to work better, especially on like kind of, we'll say like consumer grade GPS receivers.
Yeah, so it sounds like it's just purely the geometry or physics or algorithmic-based approach for SSR that just by the way it's being calculated, even though it's more sophisticated, which is fascinating to me, even though it seems like it's a more sophisticated approach, it just is limited in how accurate it can be. And that's why network RTK can get you down into the centimeter level, and SSR just can't get there.
Yeah, it's the purpose of what it was designed for. SSR is really for these very large scale baselines. And that's great if you're trying to cover large areas with a relatively sparse network. If you have the density, it's like network RTK is always going to give you kind of faster fix times, more accuracy, et cetera.
Cool, awesome. Back to the OSR for a second that we touched on earlier. It's obvious, at least to me, on a single baseline, that's an OSR-based solution. It's the observables from a fixed station and the receiver that's actually on the device. So do you classify network RTK as an OSR solution too?
Yeah, it is definitely an OSR-based solution. And the reason that we use that classification is that the way you interpolate is really at the observation level. The real distinction is that in SSR, you're taking those observations and you're actually decomposing them into these kind of like physics-based buckets.
And there's 5 buckets, if I simplistically.
Yeah, you have basically the orbits of the satellites. You have the clocks that are running on the satellites. You have ionospheric models, and those can have many parameters associated with them. And then similarly, you have tropospheric models, and those also can have several parameters associated with them. On top of that, there's even basically the biases that each constellation and frequency on those constellations have. So you need to get all that right in order for an SSR system to work, because like every single one of those components like contributes to this model of generating a synthetic observation somewhere.
Got it, got it. So network RTK is OSR because it's working on the observables themselves and interpolating based on that, where SSR is breaking the problem down into these 5 different buckets. I'm sure I am simplifying, grossly simplifying, and trying to model each of those individually.
Yes.
To figure out the data needed for the receiver to calculate the position.
Exactly right.
Excellent. All right, next mystery for me, or was a mystery for me, and I think I have it now, but we'll see. VRS.
Yes.
So a lot of people we talk to directly equate VRS with network RTK. But I don't think that's 100% accurate.
Yeah, so it is, it used to be that way before SSR became more popular. And so, if we were talking 10 years ago, SSR solutions were still kind of mostly in research. It was like not quite something that people were doing in production. Now you do have this general family of correction services known as VRS, virtual reference stations. And what that means is that I am going to give you something as a rover that just looks like a single base. And the problem is, as a rover, I don't actually know, is that a real single base, like an actual base station, or is it one of these generated things? And like we just spoke, you can generate a virtual base station using network RTK, or you could generate it using SSR. And so to a rover, it looks the same, except that the actual like properties of how those signals come out actually are different. And so this is where you can get into trouble depending on the capabilities of your rover and RTK algorithms, et cetera.
Yeah, not to drift too far into SSR land, but I can't help myself when we're having conversations because I learned so much about this. So if I could add, and correct me if I'm wrong, one of the values of using a VRS solution in SSR land is given the way SSR is breaking down the problem, you actually need software that is custom. There are no standards today on how to actually solve that equation to help a receiver understand where it is. So software typically would have to sit on the receiver, custom software. With a VRS, we can actually fake out the receiver.
Yeah, that's basically nail on the head. Like, so in fairness, like there are some standards for SSR, but it's like everything, there's like 8 standards, so is that standard?
Yeah.
And for effectively these VRS-based SSR solutions, the idea is that they're implementing what looks just like this original thing, single baseline, so that they can be just compatible, like server side is a different way to think of it. And so that makes a lot of sense. If you're an SSR vendor, you just kind of make it look like your solution is a something that works. And like we do this today with virtual RTK as an example.
And so any RTK capable receiver can consume this type of correction.
Correct.
With no changes to it at all.
That's right. And like you said, the downside of it is that since it's not a single base, it will never quite have the performance characteristics of an actual single base.
Yeah, gotcha. Okay, now this is the topic that I think has, unfortunately, a lot of FUD in the market, and really want to spend some time on this one. And this is the question of density. Mm-hmm. When we're looking at network RTK models, I think and I'm going to forget the term for it, I think one of the challenges is that, not models, the geometry of network RTK. The ionosphere itself is not, I'm going to forget the term for it, it doesn't follow a pattern, a consistent pattern in between distances. It's not well correlated, or you will know the right word for it. And that's just the way that works. Like the ionosphere is just that way. And so the farther you get apart, your stations, you're guessing more and more about what is happening at that point.
Yeah, I think so. Maybe a different way to say it is that there are parts of the ionosphere that are relatively predictable, and we have models for them, and like they're not really all that proprietary. Ultimately, like they're things that the GNSS community has used for many years. Even in standard GPS, we have this thing called Colbert, which is a model that basically every receiver uses. But it's very blunt. And so if you think about like the effect of the ionosphere, maybe let's say we account for 80% of it. I mean, still that leaves, many, many meters of error. So the challenge is how do you account for as much of it as you can?
Yeah.
And so one way to think of it is that there are kind of like low frequency parts of the ionosphere spatially. So that means that, okay, we can predict that a big chunk of ionospheric activity is moving over something like the size of a state, and so that allows you to now have these biases incorporated if you were doing something SSR-wise. However, there are often high frequency components, and these basically are little disturbances. And when you think about why does the size of the disturbance matter, well, that ultimately breaks this core assumption that the base station and the rover, if they're close, the ionospheric effect is common mode. And so if that assumption is wrong, then guess what? The receiver doesn't know that, and effectively you now have this leftover error in the calculation. And that directly will translate into position error. So effectively, these models, they're very good at figuring out how do I better represent that larger ionospheric thing that I was talking about. But when you get into those high frequency components, it becomes effectively like trying to predict the weather. And if you don't have lots of weather stations, how do you know if it's raining in, here in San Francisco, in one district in the Mission versus in the Castro?
Which may be a good segue into the troposphere itself, which is the weather. And but I don't think that has as much impact on the overall error, if I remember correctly. It still has some.
Yes.
But it suffers from the same thing, where you can have a storm somewhere, and I think it's the wet error or something related to that.
There's dry, wet components, yes. And I mean, similarly, yes, the troposphere has predictability within it. And the idea is very similar, though, where there are high frequency components and there are generally large area or low frequency components. And so it's much easier if you have a dense network to know what these high frequency components are. Yeah. And that is it's a little bit in the weeds, admittedly, but some companies really like to claim oh yeah, you can have super wide baselines, and that might be true most of the time, but then all of a sudden you have some high frequency component that shows up, then guess what? You're going to have impacted performance for that period of time.
And tying that back actually to single baseline, just the logic of it is I have this picture in my brain too of this very stretched out map, if you will, the geometry that you're trying to create. And the notion with single baseline is that you're close enough to the actual station that those correlations are much higher. I think spatial correlation might be the word I was looking for.
Yes.
Those correlations are much higher, and especially if you're at 5 kilometers or 10 kilometers or 20 kilometers, essentially the ionosphere and troposphere are going to pretty much mirror at the location of the rover.
100% right, yes.
Gotcha. If you could pull up a slide real quick, Scott, one of the things I want to do is actually pull this back into research. This isn't what we've been talking about when it comes to density is not an opinion. It's backed by years and years and years of research. And there's numerous studies, you can look many of them up yourselves, in academics who have tested and seen, hey, at different baselines, how do these geometric models with network RTK actually perform? And I think the key issue there, you being also a statistician and can talk to people about the statistics curve of probability and why I think it's the excursions are the things that are really the problem.
Yeah, and I think when you go all the way to things that people care about. So if you're trying to, have an autonomous tractor or something like this, it needs to work all the time. But when you talk about, okay, what does all the time mean? That's a statistical statement. And so if something works, let's say 95% of the time, well, clearly that's less than all the time. And so the statistical way of looking at this is that you have a distribution that says, okay, well, maybe 95% of my points are going to be within, let's say, 2 or 3 centimeters. But then these excursions, or some people say, like the things that are on the tail of the distribution, those are actually where real world systems will either work or cause catastrophic error. And so when you look at how do you really qualify like the RTK system that I need, you shouldn't just look at like, what's my 95th percentile performance? It's actually like, what is that tail of the distribution so that I can have confidence that, the actual application that I'm trying to make happen is going to work. And so, yeah, I mean, you'll very clearly see that RTK, as an example, single baseline or network RTK, will have a much better 95th percentile. But the other thing of it is that the tails will be much better. And those tails really can make or break a use case.
And what we have found, and the research would support, is if you can get the density tight enough, you won't, from the math models, you won't get an excursion that will be catastrophic. Your excursion will still be in a tight enough window where the device itself will still do what it's supposed to do.
Exactly right.
It's when you get out 70, 80, 90 kilometers is where you'll start to get excursions where fortunately, the line painter is going to not paint a straight line, or the tractor is going to start going over the crops, or other things that are not really acceptable.
Exactly. And it's all boils back to just that exact concept of if your model works most of the time, then your accuracy will be there most of the time. It's like, it's pretty much directly related.
That English I can understand without a doubt. Awesome. So maybe the last question before I get to my the fun part here. Well, this has been fun, clearly, but it's a different kind of fun. Is how should people choose between the two? We've been talking to people for years about this, and a lot of it seems to be personal preference. But how would you think about it? Taking all the marketing and everything aside, as the robotics nerd, like how do you think about choosing one or the other?
Yeah, and I mean, specifically the choice between single base and a network-based solution, they both have pros and cons, is like the candid truth. And single baseline is very simple, it's very predictable, and it has this really nice benefit of being traceable, which I define that as, if you design any system, you're going to have an anomaly that happens for some reason, and you don't know if it's the GPS or something else in the stack, and you want to go back in time and say, well, what happened? Being able to go back and look at the direct data from a single base station, it's just less complicated to debug, candidly. So there are a lot of values to that, and in certain workflows and survey, you actually want to attest that, hey, I surveyed this point in the ground, it's someone's property, and now I have a full traceable stack of why I did that. Network RTK, on the other hand, also has benefits where you can potentially have robustness to a base station that had to go down for service or some other thing that happened while you were in operation.
So if you're if not attached to one, if you're receiving corrections from one and that one happens to have an issue, then your receiver is going to search for another location, or your service is going to find another location. And the result of that could be a float situation. It could be one's too far away completely.
Yeah. So with network RTK, you're more immune to those kinds of disturbances. So, there's definitely benefit there. And then the other benefit of network RTK is that it can help, especially with lower cost GPS receivers that have less complex RTK algorithms. You can get slightly better baseline performance in between stations, because you can kind of think about it as, let's say in the worst case, you're 40 kilometers from 3 stations, you're just right in the middle, you definitely have more information if you were to take the data from all 3 than just the one that happens to be, 39.2 kilometers.
Yeah, yeah.
And so there is benefits to that in the case of, more or less being averaging kind of the data from all of them. And I think that's probably one of the biggest, is just, when you happen to be at that cusp of performance, network RTK has some benefits.
Yeah, and that could be a deep dive at some point, because we've touched a little bit on that topic with I'll just call them the lower cost receivers, or the receivers that don't have as capable a positioning engine on them, essentially. And I still don't understand how, but the network RTK approach does provide more information, or that helps that receiver resolve itself better in its location. So a lot more to that, and a lot more to unpack at another time. So that was fantastic, Aaron. I really appreciate it. Great information. You've helped me so much in the last 2 years really understand how all this stuff works. Hopefully it helped everybody here. Now I'm going to get to the second fun part of this, which are you aware of the Colbert Questionnaire? You do not watch the Colbert Show. Okay.
I do on occasion, but I don't know if I know this.
So we have a series of questions to have our listeners here get to know you better.
Oh boy.
And this will be a little bit of rapid fire, but you can think for a minute, but not a lot of depends and et cetera. So, and literally Aaron has no idea what's coming next. So you ready? Question number 1. Code phase or carrier phase?
Carrier phase.
All right. Float solution, acceptable or offensive?
I'd say it's acceptable.
Favorite constellation?
I mean, GPS.
And why?
It's the OG.
It's the OG. All right, good enough. The most overrated sensor in robotics?
Oh, man. Yeah.
He's going to make somebody angry here.
No, I mean, I was going to say, somehow I'm going to make people angry.
Or underrated. Take your pick.
Okay, no, I'm going to say the most overrated is solid state LiDAR, because I haven't seen it yet in production. So
That was a very safe answer.
Sorry.
All right, most underrated sensor then.
Well, I mean, I'm biased, but obviously GPS.
All right, awesome. VRS, which we touched on. Genius or hack?
No, genius.
Okay. What's your favorite residual to stare at?
That's a good one. So this one is a little unique because, what we do a lot of is we don't just do GNSS, we also do inertial fusion. And I actually love looking at the residuals from that.
That's why I asked.
There's something magic about a sensor that only knows how to think about its relative motion and a sensor that only knows about absolute motion, and then being able to get the information that those two are complementing with each other. And I think that there's a beautiful dance in there that, I don't know, when you see the math actually work, it's very cool.
Awesome. See, we're getting to know Aaron so much better. What's the one thing that actually improves accuracy, but no one budgets for?
Calibration.
It's another topic we could dig into.
Yes.
If you could eliminate one error source forever, what would it be?
Well, forever?
Forever. Never to be seen again.
I mean, if I could eliminate, basically make it so electricity worked as if it were in a vacuum, then I guess we may not have a business for the correction network. But it would
all right, I don't
predictable.
understand that answer at all, but we will move on. There are three more. We're getting to the end. When we say ground truth, whose ground are we standing on?
That is one of those questions of there are many various opinions, and I don't even think that the survey world agrees, and it's constantly changing. So, yeah, it's funny when you talk about ground truth, you have to also talk about what time your ground truth was in. So, another topic.
Yes, because there is no one ground truth.
Yes.
When ambiguity resolution fails, do you blame geometry, the ionosphere, or yourself?
Yes.
Okay. All right, last one. Describe your ideal localization stack in 5 words.
Can I just say 2 words? It depends.
Nope,
Okay.
you have to pick.
So I'd say tightly coupled GNSS, inertial, and computer vision.
No, that was a few more, but that's all right. That was
Yeah.
pretty tight.
Yeah.
That was pretty tight.
I
Awesome.
think I got 6.
Awesome. You're a great sport. That was fantastic. We're going to record those answers for all posterity. Sparse versus dense is depending on the latitude. So high latitude, he says, dense is 30 to 40 kilometers and sparse is 80 kilometers. Does that make sense? Sparse versus dense depends on the latitude.
Yeah, no, I mean that's fair. It goes back to the whole properties of what we're talking about working over these longer periods. The Earth has general areas where you can make those assumptions that they hold for longer. So you do technically want your geometry to be different at different latitudes, but it is what we're talking about here is like in the average case.
Awesome. Thank you, Joel. From Dave, if short baseline is the most important, why would network RTK be better than a local base right next to you? We figured we'd get a question on local base station.
Yeah. So, I mean, local bases, if it's so local that you're talking, you can see it, sure. I mean, effectively, the network RTK solutions are going to be nearly identical. And to be clear, that'll be true even in a real network RTK solution. So if you happen to be using, let's say, our network RTK solution, and we have a base station on the mall across the street, which happens more often than not, you'll basically have identical results from the network RTK or from that single base. The benefit is the redundancy. So if something happens to that local base station, you have to know something happened. So if it's your own, that can be hard. Like, even just someone bumped it and thought it wasn't a big deal. That happens more often than you'd think. And then the second problem is that if there's an equipment problem, your whole job site stops.
Yeah.
And so network RTK gives you that kind of insurance.
Yeah, and I think the one related topic we touched on this is where network RTK can actually outperform single baseline is more at say a 10 or 20, 30 kilometer range where the receiver isn't robust enough to really do as well with a single baseline solution than with a network baseline.
Exactly.
Thanks, Dave. Really appreciate it. Mike, I'm reading these without even pre-reading them, so Scott, I'm hoping you're qualifying these. How does a network RTK provider spec out the data quality? And in parentheses, evaluation of accuracy and precision for a rover at a given distance from the network.
Oh, okay, interesting.
So how do we spec out? And we have a network RTK solution, right? So how do we think about data quality in a network RTK environment?
Yeah, I think there's 2 parts to that question. So there's the data quality that we have coming from our base stations, and there's a whole bunch of checks that we do to make sure that that data is good. And it ranges from looking at the actual observation data and does it make sense relative to other things that we see, and then uniquely to point 1, we even have like mechanical monitoring, things like motion sensors, et cetera, on the base stations. Now, the other side of that question, though, is like, how do I know how my rover is going to perform on your network, that data quality? The honest answer is that it's actually very dependent on your rover and how it's implemented. High level, though, the spec is usually that there's a RTK capability, let's say, of like 1 centimeter at like a very short baseline, and then you have like a part per million number that's the slope that's linear with distance, So that usually you can find in the spec sheet of the RTK receiver.
Yeah, and one thing this is not an advertisement for 4.1 in any way, shape, or form. It's just the reality of the data in has a high factor in what comes out.
That's right.
The more that whoever your provider is understands about what's going on at the base station side and can do the monitoring and understand if that's bad data to begin with,
Yes.
really will ensure the quality. And that's why we install all of our own base stations, because we want to control that.
Yeah,
end-to-end.
and like the quality of the receivers in the base stations, like that's a whole other topic for conversation.
Okay, John, thank you. Thank you so much, Mike. John, the panel has not discussed the RTK network coordinate reference system.
Yes. So
I do not understand this. Thank you for asking. So
yeah, no,
go.
So the coordinate reference systems are, we colloquially call sometimes the datum that, your RTK network is in.
Now
So yes, and this is kind of a different workflows have different requirements. And so, some folks love to have things in a global coordinate frame. So like ITRF 2014. And then other folks, like in the survey community, will use what we call like a local datum. So here in the US, that's usually like an NAD 83. Now, each of those, you also have to be looking at, what epoch and everything that you're evaluating them on. So we are constantly keeping those up to date. One of the really powerful things is that we make it capable to the client to decide, hey, should I be operating in what is known as like a terrestrially fixed frame like ITRF, or should I be in a plate fixed frame like NAD 83? And I mean, the super high level way to think about this is like if I plant a flagpole in the ground and then I come back 5 years later and measure the latitude and longitude, the idea between an NAD 83 system is that generally speaking, the latitude and longitude should be the same. Flagpole didn't move. But in ITRF, actually it would move because the plates are moving. And specifically here in California, they move quite a bit. So yeah, you could see easily many centimeters of error in that case. So great question. And it's something that you really want to make sure your network provider is transparent on and makes it easy for you to configure.
And I think John had a follow-up actually after this that maybe we're talking about, because we didn't really spend any time on system design. Again, a whole nother topic we'll get into, but he had asked a question about antenna calibration. I think, so maybe in the context, I'm not sure if you're asking that in terms of the base station itself or the rover or device, and maybe we stay away from the device rover because that's a whole topic on system design, et cetera. But the antenna in term, let's assume he's talking about the base station calibration.
Yeah.
Is that a thing?
Oh yeah, definitely a thing. I mean, especially when you get to multi-frequency and centimeter level things, antennas, like, yes, it's a physical element, but when you talk about, okay, it's 1 centimeter or something, like 1 centimeter from where? And so there's this concept of a phase center, which is literally like where on the antenna is the L1 or where is the L2 or L5 like signal like referenced. And so good quality antennas, they'll generally be relatively tight, but you still need to put that into the input formulation of your network RTK model. So we do all those things, and we actually have our base stations like calibrated on like a robotic arm, and then you can actually not just get the frequency phase differences, but also the differences that happen as a function of elevation and azimuth. So long story short, there's a whole calibration that happens that lets you effectively null out the like properties of your antenna so that you can have it be more of an idealized, all of my signals appear in this like point. And I mean, this is pretty common, I would say, across professional, network RTK type of operators.
Awesome. Great question. I learned something new there too. I think John's also asking some questions specific about point one. Happy to answer those. Hopefully, we'll reach out to you. Hopefully, we can find out who you are or reach out to us, because I don't want to make this too much of an advertisement about point one. But one clarification I will provide, because it's a very simple answer, is virtual RTK network-based and true RTK single base. And the answer to that is no. True RTK can be delivered, is the way we look at it, either through single baseline or through network RTK, and it's your choice to deliver either way or both ways. In that sense, the virtual RTK solution is our SSR decimeter level solution. Oh, so let's end with this one. It's a little broader than just network RTK, but this is something that we get a lot, or you get a lot, is around, let's talk about, and I'm going to paraphrase what you asked, Joel. Does all of this not matter when we have LEO?
So LEO is an emerging thing. So let me just provide a little context. LEO is just like a distance of orbits around the Earth. It's much closer than GPS, which is, I guess, technically like a MEO system. LEO constellations, they have very different properties than GPS. The satellites effectively move much faster, and the constellations have to be much more dense to get the same number of satellites because they're closer to Earth. So technically speaking, there aren't active LEO navigation systems out there yet. Technically, there is a way to navigate with Iridium, which is a very, very old LEO system that's out there. And I actually worked on some of the initial things to do that, almost 15 years ago. And, it's a complementary technology. Now, there are companies that are working on building pure LEO systems. They have the same properties, though, that you still have to compensate for things like orbits and clocks and ionospheres and all these things. So the properties work the same. Their main benefit is just, it's pretty simple. They're much closer to Earth, so the signals are much stronger. So it helps in things like, canopy and indoor. But for the precision market, you still need to have really good quality carrier phase. And so I think you'll see some benefits, but it's not going to be, a replacement for indoor navigation systems, as an example. I think the long term is that you will have, certain systems that will use LEO as a complement to traditional, GPS and GNSS. But it's, I think, unlikely that you're going to end up with pure LEO systems aside from unique defense cases and things like that.
And you need specialized hardware for it on the receiver, or it can use the off-the-shelf RTK receivers that exist today?
They would, well, no, I mean, it's like the receiver definitely needs to be capable of working with these LEO systems. In general, it depends on whose system it is. It depends on, ultimately understanding what those kinds of modulations are used on those signals. And yeah, there's even a question of, what frequencies they're transmitting at, do I need a different antenna, et cetera. So in the case of Iridium, yes, you would need a completely different antenna because it's a different frequency than GPS. But I do know some companies are working on stuff that can potentially even coexist in similar bands. Yeah. So it's just kind of, it's very early stage. And I think it's great to see that there's, I would say, modernization and a diversity there because, frankly, satellite navigation is I think really important part of everyone's daily life. And so we need to be investing in that.
Awesome. Thank you. Thank you, everybody, for your questions. Those were awesome. I learned some new stuff myself. And thanks again, Aaron, for joining the show.
Yeah, thank you.
And we'll see you next time. Thank you, everybody.
Thank you.